last Wednesday, and we looked at resonance within that, right? What electrons did we move when we looked at benzene for that resonance? What? Okay, which pi bond? We eventually touched every single one of them, but we did not start our resonance with every single one of them. Okay, started with the upper right.
On the board, yeah.
You mean just the right one? That one?
Yeah.
Okay. I may have drawn it slightly differently. Yeah. Okay. Why did we pick that pi bond? Why start with that one and not say this one?
Arbitrary.
Or this one? Right? It arbitrary. Didn't matter. Why does it not matter?
Because they all do the same thing.
Kind of, sort of, all the same thing.
Because if you move either one of those, it's going to have the same effects to like the electronegativity of the. So if you move the next bond to the next atom.
True, but by making that statement, I'm getting the feeling that you're saying you don't get a different structure.
Yeah.
But resonance is pinned. If I move the electrons with the black arrow pointing to it, I'm going to have a negative and positive on those carbons up in the upper left-hand corner. If I move the one with the purple arrow, I'm going to get negative and positive on carbons on the right-hand side of the structure. Those structures, in resonance terms, are different because we're putting charges on a different atom. Okay. So I'm getting a quote-unquote different result. Why does it still not matter which one I move?
Because when you either one of those you change, you're going to end up with the same result.
But we just said you don't get the same results. The negative and positive charges are held on different atoms.
But it has the same effect on them.
Work on that E word for me. Same effect. It's another E word that's an important one to use. They have the same energy. Those structures result in the exact same energy structure. So it doesn't matter which double bond I use because all the double bonds are of equal energy. So I can use whichever double bond I want. Okay. Why does this become important? Well, what happens if we shift down to the next structure? Okay, so a couple people talked to me in office hours. There were a couple structures that came out there that we could look at, and I just picked this one to start off with. What electrons can we move in that structure? Pi bonds and lone pairs. Okay. Which is higher in energy, a pi bond or a lone pair? The pi bond is technically higher in energy, and that's a difficult question at this point because we haven't looked at orbital energies and where our electrons are located and all of that. But you're right, referencing the pi bond is higher in energy. Okay. In this case, are all of those pi bonds the same energy? If they're different energies, is there one I should be looking at moving first?
The furthest one?
Furthest from what? So that
From
doesn't
the lone
quite
pairs.
work for me.
The furthest from the lone pairs.
Okay, why?
The least amount of energy is being pushed on or forced on them.
You're suggesting as we get less of an energy difference here if I decide to move those electrons, say, to that carbon. Okay, and actually I'm going to fix that arrow. I don't like that arrow. I'm going to move them the other direction. Why would I move them the other direction? Why should I move them the way I've got shown now? No, we're not going to have an octet issue here, unfortunately. If we draw the result of this, it's not a bad idea. No, this doesn't look the prettiest, but it's okay. We're still going to lose an octet, which is fine. We'll just kind of accept that. We haven't exceeded an octet, so we're okay there. Why move the electrons that direction as opposed to having moved them the other direction where we got the negative charge up at that position? Why is the bottom situation better than the top? Sort of. And hint, this is based off of rules you already know. It's irritating.
Does it impact the shape of the molecule?
No.
Because there's nowhere to go.
Because the electrons are moving toward the most electronegative atom.
Oxygen is exceptionally electronegative. Where are the electrons going to move? Towards the most electronegative atom. So that bottom case probably makes a little more sense. We're shuttling the electrons towards that oxygen. Okay, so now let's go back and evaluate that arrow. We're saying to use the pi bond all the way back there first. Okay, because we're saying that that carbon here is feeling some electronegativity pull from the other oxygen, causing electrons to be shuttled towards that carbon versus the other one. And that then makes that pi bond the most reactive pi bond. Everybody agree with that statement?
Could you repeat that question?
That pi bond is now the pi bond that we should be starting our resonance structure with, because it is the highest highest energy pi bond. Why are you saying no?
It's further away from oxygen?
It's further from the electronegative element. Okay? We're looking at carbon versus carbon. The electrons in a bond between carbon and carbon are shared where? Which atom do they prefer to exist on? They're equal on both, so we can go neither or equal. We're going to get the same result. Why would we have the electrons shifting ever? We wouldn't. Okay? So the electrons in that pi system are already relatively stable. Is there a more reactive pi bond? The one closest to the oxygen is probably going to be a little bit more reactive or higher in energy. Why? It's closer to the electronegative element. That pi bond is most likely to be polar. That should be the start of me drawing out my resonance structures. Not with looking at the carbon-carbon pi bond. Okay. We can do a little bit better actually in referencing these. Let's not reference them as the carbon-carbon pi bond or the carbon-oxygen pi bond. Let's refer to them based on their functional groups. My resonance should not start in the alkene. It should start in the what's this functional group? Sometimes it's helpful if we tag on that missing element. Alcohol is hydrogen bound to oxygen. We don't have an alcohol. We have an aldehyde. We should start our resonance drawings looking at the aldehyde because it is already most polarized because of that electronegative oxygen. Kind of makes sense? So we went from a case where it didn't matter which double bond we used because they were all of equal energy to now being very, very selective in the double bond we're using, okay, or our electrons, because it's higher in energy. Questions about that? Okay. So now I'm just going to erase everything. I know you were joking, so don't make those weird noises. It gives me a heart attack. What happens now? What electron should I be moving first? Electrons I'm allowed to move are pi bonds and lone pairs. What are you thinking, Stephen?
I'm thinking one of the lone pairs on the negative oxygen.
Why should I start with my electrons there as opposed to one of the pi bonds?
It's higher in energy than a pi bond.
If it's higher in energy than a pi bond, I should start there first. Okay. The pi bond is using p orbitals technically. Our lone pairs are held in hybrid orbitals, okay, which are lower in energy than our p orbitals. I know, that's kind of a stretch because we haven't officially looked at all that bonding mumbo-jumbo stuff yet. Okay? But if we take that just at face value, we said we shouldn't look at the lone pairs, we should look at the pi bonds first. And yet now, what am I looking at? The lone pair first. Why? It's charged. Charge is inherently higher in energy than everything else. We will start with our charge and neutralize that charge as quickest as possible. Okay? That is where I'm going to start my resonance. If I had instead started the resonance, well, here, let's actually draw the result of that. Okay, and we'd necessarily have to move that one across. Assuming I didn't lose any carbons in there. We would end up with that structure. Yeah? What if I instead said, well, that pi bond is more reactive? What's the result I would have gotten? Why is my purple one worse or not quite as good as my blue one?
More charge.
There is more charge located in the purple one. More formal charge. More formal charge is one of our Lewis structure bad things. We want to avoid generating as much charge as possible. Okay. Is it inherently obvious? No, not by a long shot. Okay. But when you're trying to go through and rank these and decide what resonance structures you can draw, start with your highest energy electrons. Okay. At this stage, we don't have a definition on why they're highest in energy, but those are going to be your negative or positive charges. Okay. Then you can move to pi bonds. Then you can move to lone pairs. Okay. Or just general uncharged lone pairs. That is going to be the easiest way to generate all of your best resonance structures without kind of running into other issues. Okay. Is the purple one still a resonance structure?
Yes.
Yes. If you drew this as a valid resonance structure for this compound, you would get marked wrong in your online homework assignment. Okay? Because it's not one of the better resonance structures. But without a context of knowing why that one was wrong, you're kind of lost. It's going to come down to finding your highest energy electrons, stick with those to do your resonance, that'll get you through it. On a test, I still have not figured out how I would grade this. If you gave me all the resonance associated with the purple one, I don't know what I would do. Okay? You would actually have stumped me. Okay? It's going to be really hard to figure out how to assign points there. It's technically not as good, which is why I would run into an issue. You would have to lose some points. But as long as you drew everything correctly, it's kind of an oddball thing. Yeah. Okay. Other questions on that? Those are just some of the things I saw pop up. Okay. Intermolecular forces. Okay. This is something that I find kind of abhorrent within general chemistry, and it kind of, as I increase the interaction, I'm now saying, oh, it's a stronger force. Well, now that it's a stronger force, I shouldn't really call that London dispersion, because London dispersion is really no force. So we gradually shift up until eventually we say, oh, it's a dipole-dipole force. Okay. Then we shift up and we say it's ionic. Why did I skip hydrogen bonding? Okay. Hydrogen bonding is a dipole-dipole force. Okay, by definition. You cannot have hydrogen bonding unless you are a dipole-dipole. Okay. So we move from a dipole-dipole all the way up to an ionic. Ionic is a nasty, nasty gray area. Okay? That one becomes really, really confusing. Because we can have an ionic interaction that doesn't really qualify as a bond. It's still this kind of weird thing that we say a force. But if we make it just a little bit of a stronger interaction, we say, well, now it's not really a force. They're actually kind of sort of sharing electrons. And by that kind of sort of sharing of electrons, that means I'm no longer looking at this weak interaction relatively. I'm now looking at the formation of a bond. As I make that interaction between those two atoms stronger and stronger and stronger and stronger, I shift all the way down to a nonpolar covalent bond. Okay? And this concept is a bit weird, because when you think of bonds, what do you think of as the strongest bond? Ionic. Fair enough. What's your reason for thinking ionic is the strongest bond?
Because it's completely capturing the electron. And so,
If I come up and steal all of your money,
yeah.
does that mean that interaction was the strongest? You and I are getting along really, really well?
Well, I'm not going to say that we're getting along, but you have my resources.
What we're looking at is the strength of that interaction. I can take your money and I leave. Okay? We're not interacting at that point. I take it and I walk away.
Or I could chase you down.
You could chase me down. Okay? And that's starting to now show some kind of interaction. You can chase me down and start saying, no, give me some of that money back. Yeah, polar covalent. You can chase me down and negotiate. Now we're actually agreeing. We'll share the money and we will buy together something to now enjoy our newfound camaraderie. Okay? But the ionic interaction is straight up stealing. Why is that considered the strongest bond in most students and even, check the internet, thoughts? A classic ionic compound. Give me an example. Sodium chloride. I completely agree with you. That's a good classic example. Give me a classic non-polar covalent compound. Methane. Okay. Why might we use this to now say ionic bonds are stronger than non-polar covalent bonds? What do you know about salt versus methane?
Salt, it dissolves in water.
True, but that's not how you're getting them to interact with something else. Let's avoid them interacting with something else. Not because you're wrong, but that makes it more difficult. What do you know about salt? I'm going to guess that you said solid there, but maybe you just repeated the word salt. What could you tell me about methane?
Gas.
It's a gas. Well, why is methane a gas, but salt is a solid?
Because of the melting points.
Doesn't that mean that salt is holding on to other salt molecules better than methane is holding on to other methane molecules?
Yeah.
Which would then, by definition, mean that our ionic bond and our salt should be stronger than our London dispersion force in methane. Our melting points and boiling points are not based off of bonds. They're based off of forces. If you look at the strength of a covalent bond, it is much, much stronger than the strength of an ionic bond. But what we can visualize comes back to these phase changes. And we start to apply those phase changes to the bond character. When we boil methane, or when it turns from a liquid to a gas, what happens to the bonds in methane? Nothing. Why? Because we can't break the bonds with that energy. What happens to the bonds in sodium chloride?
They melt.
Melt. They break. We are breaking bonds when we melt sodium chloride or dissolve sodium chloride. We don't break those when we melt or boil, that's our other phrase, our methane. What we're breaking is the intermolecular force connecting one methane molecule to another methane molecule.
How can you boil a gas if it's already in a gaseous phase?
You wouldn't boil a gas, you would boil the liquid. And the boiling point for methane is incredibly low, which is why we see it as a gas.
Okay. I was just making sure I didn't
Yeah,
miss,
no.
chapter 2. You can
So when we're looking at our phases, we have to be careful to interpret the forces. The issue is, how do we get to those forces? That comes from understanding something about the bond nature. When we look at methane, we have a nonpolar covalent bond, which means the charges on the carbons and the hydrogen ends up coming at as nil. If there is no charge on those atoms, do they need to interact with other atoms? No. So they don't interact. They have a very weak attraction for each other, which means when I add just a little bit of energy, what happens? They peace out and they separate away from each other and move to the liquid or to the gas phase. We're breaking the forces, not the bonds. How do we know we have a bond or a force? Arbitrarily, we drew a line and we said on this half of the line, we are forces, on this half of the line, we are bonds. Completely arbitrary system that falls right through the middle of the ionic interaction. Okay? This is important because what you're trying to do is now be able to classify how these molecules can interact with other molecules, which is ultimately going to come back to their forces. Yes?
Is it really arbitrary though? Because, I mean, there's like the bond between like the sodium chloride, that's an ionic bond. But then the interaction between other sodium chlorides is an ionic force. So it seems like to me there's some sort of distinction between the two.
When do you have a bond? When do you have a force?
When the electrons are,
Yeah. Particularly with an ionic bond, which by definition is they are not sharing electrons. You're shifting when you move from bonds to forces. Bonding is by definition a sharing of electrons. Okay? So we run into this weird gray area because we're still referring to ionic bonds, but is it really a bond when by definition it's not sharing electrons? So your ionic bond slash force is a very, very gray transition-y area. And we kind of apply it on both sides depending on what we're looking at. Okay? Fun thing about our ionic bonds and forces is how often are we going to have to worry about them in organic? Not a whole lot, because when do we have ionic bonds? Metal and a non-metal. How often do we deal with metals? Not very likely. Okay? So we don't have to stress about our ionic bonding situations quite as often. Okay? So how do we apply this? Well, we already applied it to our melting points and our boiling points, our phase transitions. The stronger the attractive force between molecules, the more energy we need to put in to break those molecules away from each other. That energy we would quantify. Those of you that read the lab and were wondering, what the hell, how do we quantify energy? We quantify that energy that we put in as temperature. The more heat we supply, the more energy we've put in. We move to a higher temperature. So we can refer to our melting points and boiling points based on increasing forces, increases the melting point or boiling point. What happens with solubility? It's similar forces interact with similar forces. Why not similar bonds? Solubility is by definition mixing one species with another species. If I look at similar bonds, what does that mean?
It's the same species.
It's the same species. They are connected to one another. We're no longer looking at solubility. Okay, so it's a force application. Vapor pressure is a really nasty one because vapor pressure is actually an understanding of what the boiling point is defined as and how that ties back to vapor pressure. The only reason I include that is there's a nasty question in the chem235 final that's fun to talk about with students that usually blows people's minds. Okay? If you want to ask about that, we can talk about that later. This also contributes to reactivity. Okay? So it's coming up with a balance. How do we apply these forces to nail everything down? Questions on any of that? Okay. Then, since you don't have any questions there, this is probably just review. When we're looking at our melting points and boiling points, is the energy necessary to generate that phase change. That energy is the energy necessary to break the intermolecular forces, because the intermolecular forces are what are resisting the change. Okay? So if we have a higher melting point or boiling point, what would we expect of our intermolecular forces? They should be very, very strong. Okay, so let's take a look at some quick examples here. We have the structure for, don't all jump in at once, water, thank you. And the structure for, see, I gave you the easy one first. You haven't been studying your, did you say not water? I was going to say that's a pretty classy answer. Okay, it's actually naphthalene, straight out of the lab. That's actually why I kind of threw it at you. Okay, So, based on intermolecular forces, which of these should have the higher melting point or boiling point? Water. Absolutely. Water has hydrogen bonding. Naphthalene has London dispersion. So we would predict water to be solid or liquid before naphthalene. What is the phase for water at room temperature? Liquid. What's the phase for naphthalene? Solid. Why? What does bigger have to do with anything?
More electrons mean more forces added up together.
It's not just the strength of the force, but how many of those forces are there. You could probably beat up a little 5-year-old kid. Okay? That sounded better in my head. But if I threw 1,000 5-year-old kids at you, you probably would get beat up. Okay? Okay? Why? There's too many of them. It's not just the strength, but how many. When we move to naphthalene, it is an incredibly weak force in London dispersion forces. But there's a lot more of those London dispersion forces because there's more atoms. Okay? So when we're looking at these, we can't just say, oh, it's just the strength of the force. We also have to look at how many are there, which means, is this a perfect science? No, it's an art form. You look at it, you take your best guess, and then you test it and see what happens. Okay? Solubility. It's the ability to mix two individual species with each other to generate a homogeneous solution. Okay? What would help this? Like forces. Why? If I take water and I want it to interact with another species, what has to happen to all of the interactions water currently has with other water molecules? They must break. They must break to interact with that new species. Well, if it generates a weaker interaction with that new species, would water consider doing it? No. It needs a stronger interaction. Okay? So it's all about a comparison in those forces in deciding how it matches up. Okay? Our general rule on that was like forces dissolve like forces. And then if I remember correctly, not quite remembered correctly, we can also run into this idea of solvent terminology. Okay? We started this whole class off with polar and apolar, horrible idea, don't do it. And yet, what am I now doing? Throwing polar and nonpolar up there for our solvent terminology. It is the largest classification for our solvents. It's very hard to avoid using this terminology. We kind of have to just stick with it, but realize it has some massive limitations. What type of forces would we expect for a nonpolar solvent? London dispersion forces. Okay, so it's not a comparison. We're saying a nonpolar solvent should have very weak interactions with its environment. So we would expect London dispersion forces. For a polar solvent, okay, we could jump to ionic. I completely agree with you, but I'm going to immediately cross that out. Why?
We're not using metals.
Not a bad jump, saying, hey, well, it's organic, we're going to ignore metals. There's a different reason.
Polar bonds.
Our solvent needs to be a liquid, and most ionic compounds, as you have astutely pointed out, are solids. It's very difficult to dissolve something when you're using a solid to dissolve it. Okay? Are there such things as ionic liquids? Yes. We can take salt and we can get it into the liquid phase at 900 degrees Celsius. Cool. I can now run my experiments in a 900 degree Celsius bath. Most organic substances tend to decompose or combust, get destroyed in that temperature, so we tend to avoid it. Are there such things as room temperature ionic liquids? Yes, you don't want to work with them. They suck. Yes, that's experience. So, standard solvents, as polar as we're going to get, is going to involve dipole. A few of you shouted out hydrogen bonding. Okay. Why would I specify dipole? Hydrogen bonding is a dipole-dipole force. The dipole-dipole interaction is a much broader classification for polar. But what's at the extreme end of that polar solvent? Well, hydrogen bonding. But I can have a solvent that has a dipole-dipole polarity that is not hydrogen bonding. So what we'll end up doing is subclassifying the term polar into two other categories. Those two other categories would be, those of you who had the slides can kind of cheat. Those of you without the slides can probably guess at this. How about hydrogen bonding polar or dipole-dipole polar? Anybody happy with shouting those out every single time? No, so let's invent a new word. Hydrogen bonding. When we're looking at that, hydrogen is effectively being what? What charge? What is another name for H+? A proton. So our new solvent terminology is protic versus aprotic. Aprotic meaning not protic. Protic meaning we have protons. When do we have protons? We do not have protons always, in this context particularly. Protic is our hydrogen bonding situation. Aprotic is our dipole-dipole situation. Would I ever have a protic nonpolar solvent?
No,
Why not?
because it's all the way to the left.
Our protic solvent is by definition dipole-dipole, which by definition is polar. Okay? So by saying protic, you are immediately implying polar. Can we have an aprotic nonpolar solvent? Yes. There's lots of cases of that, and that's in fact where most of our experiments will sit, is with aprotic polar solvents. Why do we want them to be polar? We want to dissolve more things. Water works at dissolving things because a lot of things are polar. Okay, so in this case, we have dimethyl ether. Okay, we could even throw in, since a lot of people, I'm sure, will reference this compound as nonpolar, methylene chloride is not a nonpolar solvent. It is actually quite polar. It just happens to be aprotic. Okay? When we run a reaction, we have to decide, do we want a solvent number one, and then what characteristics do we want that solvent to have, be it polar, apolar, okay, protic. So just be aware of that extra terminology popping up. Questions? Positive. Oh, there it is. It's positive we had a quiz, so there's a quiz.